Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
For decades, we have been staring up into the infinite dark of the cosmos. Listening.
Waiting.
Right, waiting. We've built these massive dishes, these sprawling arrays across deserts and valleys, all tuned to the silence of space. And we're listening for one highly specific type of sound.
And it's an assumption the entire scientific community has held on to with almost absolute certainty.
Yeah, the idea that if an advanced extraterrestrial civilization wanted to reach out, say hello, they would broadcast a signal so mathematically precise, so impossibly concentrated that it couldn't possibly be a mistake.
Exactly. We've been hunting for an artificial whisper in the dark.
The ultra-narrow frequency spike.
Right. Billions of dollars, entire careers have been banked on this one idea that an alien beacon would arrive as this pristine, razor-thin line of pure electromagnetic energy.
But there is a massive problem with that assumption.
A huge problem. It basically treats the universe like it's an empty, passive vacuum. We've treated interstellar space as if it's a quiet concert hall where a single drop pin would just echo perfectly for 1,000,000 light years.
Which it absolutely isn't.
No, not at all. The reality is that the cosmos is a violently active, incredibly hostile environment for any kind of electromagnetic communication.
So that exact, pristine, razor-thin signal we've been banking on, it might actually be actively destroyed by the universe before it even has a chance to leave its home star system?
That's the core of it. Back in 2026, researchers Dr. Vishal Gujjar and Grace C. Brown introduced this concept of exo-interplanetary medium scattering, or exo-IPM scattering for short.
Exo-IPM scattering.
Yes, and it fundamentally acts as the hidden gatekeeper of alien signals.
Okay, I want you to imagine something. Imagine you are the lead engineer on an alien world. You've spent centuries of your civilization's GDP building the ultimate interstellar megaphone.
The pinnacle of your technology.
Exactly. And you finally hit send on your masterpiece of a message. It's a perfectly clear, ultra-narrow broadcast aimed right at the Milky Way. But before that pristine signal even clears the orbit of your outer planets.
Your own sun gets in the way.
Yes. The weather of your own sun, this turbulent, churning plasma of your star, scrambles your perfect message into unrecognizable static.
It's the ultimate galactic reply-all disaster.
You're screaming into the void, but your own sun is acting like a muffler.
It really forces a complete reckoning with how we understand the physics of stars and also the hidden blind spots of our own computational technology.
Because we are faced with this haunting possibility that the cosmos isn't actually quiet at all.
We might simply be listening in completely the wrong way.
So to really grasp the mechanics of this exo-APM scattering, we first have to understand the baseline difference between natural astrophysical radio emissions and, engineered technosignatures.
The symphony of chaos versus the artificial whisper.
Right. Because the universe is notoriously loud. It is screaming in radio waves constantly. But the noise a star makes and the noise a deliberate transmitter makes, they are completely different beasts.
Completely different. Natural celestial bodies and unguided astrophysical processes, they simply do not emit perfectly narrow radio signals.
They broadcast across a massive, sweeping range of frequencies.
Exactly. The universe is filled with incredibly violent, chaotic physical processes. When you look at pulsars or quasars or the cosmic microwave background, you are observing physics at its absolute extreme.
Let's break that down a bit. Take a process like synchrotron radiation, for example.
Right, synchrotron radiation. So out in deep space, you have these powerful twisting magnetic fields. When electrons interact with that environment, they get caught.
And they begin spiraling.
Spiraling around those magnetic field lines at relativistic speeds, meaning they are moving at a significant fraction of the speed of light.
And as they spiral and accelerate, they're shedding energy, right?
Yes, they shed it in the form of electromagnetic radiation. But because the speeds, the magnetic field strengths, and the angles of trajectory are just totally chaotic and constantly varying,
the resulting radiation is smeared.
heavily smeared across a vast spectrum of frequencies. It is this massive, uncoordinated blast of radio noise.
And then you throw in plasma collisions. I mean, I know there's another major source of broad spectrum noise when particles start literally slamming into each other.
Ah, you're referring to Bremsstrahlen.
Right, breaking radiation.
Exactly. This happens when a charged particle, like an electron, is violently deflected by another charged particle, like an atomic nucleus.
It essentially slams on the brakes.
And in the quantum realm, when a charged particle is violently decelerated or deflected like that lost kinetic energy has to go somewhere. It is emitted as electromagnetic energy.
So in a dense plasma cloud, you have, what, billions of these collisions?
Billions of them happening randomly at varying speeds, varying angles. The resulting radio waves are broadcast over a very broad, very messy spectrum.
It's like a massive chaotic orchestra warming up before a performance. You have hundreds of musicians, the violinists are plucking strings, the brass section is blowing random blasts of air, the percussionists are dropping things.
This absolute noise.
The sound is smeared across every possible audio frequency. There is no coherence. That broad spectrum noise is the chaotic orchestra of natural celestial emissions.
And in that environment, an engineered technosignature, that ultra-narrow signal we've been searching for, is mathematically modeled to be just a few hertz wide.
So it wouldn't be the chaotic warm-up.
No, it would be a single, perfectly sustained note on a tuning fork piercing through all that chaotic noise.
A sound so deliberate that your brain immediately registers, oh, someone is doing that on purpose.
Exactly. A natural, unguided celestial mechanism is basically completely incapable of generating a signal that is perfectly compressed into a bandwidth of just a few hertz.
So if an astronomer looks at a spectrographic signature and it presents as this pristine vertical line on a data plot, the math just dictates it must be a delivered transmission.
And that specific mathematical logic has driven the entire architecture of our search. Decades of telescope time, massive infrastructure projects, they've all been built on the foundation of looking for that tuning fork.
Which brings us to a massive structural vulnerability in how we actually process astronomical data. We have an interstellar blind spot.
A huge one.
But wait, practically speaking, it's not like astronomers are ignoring the fact that space is messy. I mean, our current computational pipelines are incredibly sophisticated.
Oh, they are brilliant.
We know about the interstellar medium, right? The diffused plasma between the stars. And we have dedispersion algorithms to clean up the signal, don't we?
We do, and they are incredibly effective at what they're designed to do. Existing detection algorithms strictly account for the distortions that radio waves experience while traversing the vast distances of interstellar space.
Because when radio waves travel through that low-density diffused plasma of the interstellar medium, they experience dispersion and scintillation.
Right. And the dispersion physics are fascinating because it's essentially this massive cosmic race where the lower frequencies lose.
The lower frequencies lose the race. I love that.
It is fundamentally a problem of speed and frequency interacting with plasma. Lower frequency radio waves interact more heavily with the free electrons in the interstellar medium than higher frequency waves do.
So there's more drag.
Exactly. As a result, the lower frequency components of a signal travel marginally slower through this diffuse plasma.
So if an alien civilization transmits a signal with multiple frequency components simultaneously,
those waves fan out over a journey of thousands of light years.
And the higher frequencies arrive at Earth first,
while the lower frequencies arrive with a measurable temporal delay.
Okay, so a sharp, instantaneous burst arrives at Earth stretched out. It ends up sounding more like a descending whistle because the high notes hit the telescope before the low notes.
Yes. And current search algorithms deploy highly complex dispersion techniques to counteract this exact effect.
They fix the whistle.
Right. Astronomers mathematically calculate the Coulomb density of free electrons in the interstellar space, separating Earth from the target star.
They figure out how much stuff is in the way.
Exactly. And using that calculation, the algorithms realign the frequencies. They shift the delayed lower frequencies back in time to perfectly reconstruct the original signal.
So we are absolute masters at cleaning up the dirt from the interstellar highway.
We are.
But here's the fatal flaw in the entire operation. These brilliant algorithms operate on one massive underlying assumption.
They assume that the signal entered interstellar space in perfect condition.
Right. They assume the structural integrity of the radio wave is entirely undisturbed between the alien transmitter and the edge of its host star's system.
The algorithm's meticulously correct for the long highway between the stars, completely ignoring the incredibly treacherous dirt road the signal has to travel just to get out of its own planetary system.
They assume the starting line is clean.
And it isn't. Dr. Gajar and Grace C. Brown's 2026 findings reveal that the astrosphere of a host star is a violently disruptive environment.
We're shifting away from theoretical computer algorithms now and diving into the concrete, highly chaotic physics of a star's environment. Because we tend to think of stars as these static, glowing backdrops.
But they are turbulent magnetic oscillators.
An incredibly dynamic, violent engine.
Right. To understand how it actually destroys a signal, we have to look at the specific agents of distortion within the host star's astrosphere.
Starting with stellar winds.
Yes. Stellar winds create a highly structured, constantly shifting refractive environment. These are streams of free electrons and protons blowing outward from the star at tremendous speeds.
And it's a fluctuating, dense medium. But stellar winds are just the baseline weather, right? You also have the severe storms.
The episodic eruptive events.
Yeah.
Coronal mass ejections, or CMEs, and powerful stellar flares.
Let's define a CME for a second.
A CME is a massive expulsion of plasma and magnetic field from the star's corona. Billions of tons of superheated plasma are literally hurled out into the planetary system.
And they carry these incredibly complex, twisting magnetic fields with them.
Exactly. So our alien engineer fires up their machine. The perfectly mathematically narrow tuning fork signal leaves the planet's atmosphere.
And immediately slams into this stellar space weather.
It hits the fluctuating stellar winds, or gets caught in the turbulent wake of a coronal mass ejection.
And this is where we see the mechanics of exo-IPM smearing, which is fundamentally rooted in optical multipath propagation.
Yes. When perfectly coherent radio waves hit a region of fluctuating electron density, they experience varying indices of refraction.
Because the stellar plasma's density is violently fluctuating in milliseconds.
Right, so the radio wave experiences rapid phase variations.
So the electrons in the stellar plasma are swirling around, they're pooling, they're thinning out instantly, and so the signal is being bent and deflected a billion different ways simultaneously.
The rapid phase variations physically scatter the photons. The signal does not just pass straight through, it takes multiple different paths through the turbulent plasma.
Because the photons take slightly different paths, they arrive at slightly different times.
And that physical redistribution of electromagnetic energy mutates the transmission. A sharp, concentrated tone is morphed into a wide, faint, dispersed footprint.
Imagine trying to shine a perfectly tight laser pointer through a violently boiling pot of water.
That's a perfect way to visualize it.
The photons don't cease to exist, but the turbulent, boiling water bends and scatters the light so severely that on the wall behind the pot, you don't see a sharp laser dot.
You just see a faint, flickering, completely smeared wash of light.
That is exactly what a star's plasma does to an alien radio signal.
The signal is shattered. This mathematical consequence is sometimes referred to as the radio silence hypothesis.
The radio silence hypothesis.
Yes. The signal broadening physically renders technosignatures completely invisible to our current SETI searches.
But if the energy is still there, if the photons didn't vanish in the boiling water, why can't our multi-billion-dollar telescopes see it?
It comes down to the rigorous physics of energy conservation and how that dictates the failure of our algorithms.
Okay, walk me through that.
Well, the plasma surrounding the star is non-absorptive. It does not actually consume the radio wave's energy.
Right.
The total amount of electromagnetic energy that left the alien transmitter remains exactly the same. The total energy is constant. However, because the bandwidth of the signal increases drastically due to the exo-PM scattering, the peak amplitude, which is the intensity of the signal at any one specific frequency, must drop proportionally.
Think of a teaspoon of jam.
A teaspoon of jam.
Stick with me here. The jam represents the total constant energy of the alien radio signal.
Okay.
If you take that jam and place it onto a tiny cracker, you get a tall, highly visible, concentrated mound of jam.
Right, that's your ultra-narrowband signal.
But the star's plasma subjects the signal to exo-PM scattering. It forces you to take that exact same amount of jam and spread it out evenly over a giant 16-inch pizza crust.
The total energy hasn't changed. You still have 1 teaspoon of jam.
But because it has been smeared across such a broad area, it becomes an imperceptibly thin, practically invisible layer.
And that thin layer causes modern automated algorithms to fail. The pipelines deploy what are called matched filters, designed to look at the cracker, not the pizza crust.
They are optimized to look for power accumulating in extremely narrow frequency bands.
They're checking millions of tiny channels, looking for a massive spike of energy in just one of them.
And if the star's plasma scatters the photons, that power leaks out into thousands of adjacent bins.
Exactly. The algorithm checks that original narrow bin and sees only a tiny fraction of the original energy.
Because the energy is diluted across so many channels.
Right. And so the algorithm fails to accumulate a sufficient signal-to-noise ratio. The signal falls below rigid detection thresholds.
The computer looks right at it, flags it as an automated non-detection, and just classifies it as background noise.
Which directly addresses the historical lack of detected signals. We've wondered for decades why the sky is so quiet.
This hypothesis suggests the sky isn't quiet at all.
Not at all. Signals might physically be hitting Earth's radio dishes right now, but because they have been smeared out by their own sun's weather, they masquerade as diffuse background noise.
We are filtering out the exact thing we are looking for because it doesn't look the way we expected it to.
It's a profound paradigm shift, but theoretical physics isn't enough to change an entire scientific field. You have to ground the theory with empirical data.
You need proof.
Exactly. Researchers quantified and proved that exo-IPM scattering actually happens by using our own solar system.
Now that is fascinating. How do you prove that a star ruins an alien signal when you don't actually have an alien signal to test it on?
You establish boundary conditions and calibration metrics. Researchers needed a baseline. They needed a perfectly continuous, narrow-band signal passing through a known, measurable plasma environment.
So they used human engineering.
Yes. They used our own transmissions as artificial technosignatures, specifically the telemetry transmissions from our deep space probes.
Like the Voyager probes and planetary orbiters?
Exactly. It's a brilliant experimental design, really.
Because we built those spacecraft, so we have absolute knowledge of their origin frequency.
We know their transmission power and their uncorrupted spectral profile. We know exactly what the signal looks like when it leaves the antenna.
And they operate within a localized plasma environment we can observe right here, the solar wind of our own sun.
Right. So observatories on Earth meticulously measured these known telemetry signals as the line of sight between the spacecraft and Earth passed through varying densities of our sun's plasma winds.
Because during certain orbital alignments, a spacecraft's signal actually has to pass very close to the edge of the sun to reach Earth.
Right. It grazes the sun's atmosphere during a solar conjunction.
And what did they find?
The researchers contrasted the data from these different alignments. When the transmission passed close to the dense, highly turbulent solar corona, they observed extreme smearing.
The pristine telemetry signal was shattered.
Broadened, just as the theory predicted. But when the alignment shifted and the radio waves only passed through the thinner, quiescent solar wind far away from the sun,
they observed minimal smearing.
The signal remained relatively narrow and intact.
So they literally watched our own sun destroy our own signals and measured exactly how much it was happening based on the plasma density.
Exactly. The result was a precise mathematical correlation between measured plasma column density and the resulting degree of frequency smearing observed at Earth's receiving stations.
And with this localized data, they created a scalable framework to estimate signal broadening across the cosmos.
Which pivots this from a fascinating physics experiment into a major crisis for traditional target selection.
Because when you take this math, which was calibrated on our relatively calm sun, and apply it to the rest of the galaxy, you slam right into the M-dwarf dilemma.
The M-dwarf dilemma. It fundamentally alters the search for life because it concerns the dominant stellar demographic in the Milky Way.
M-dwarfs or red dwarfs.
Right. They make up approximately 75% of the stars in our galaxy.
75%. That is a massive majority. Statistically, any comprehensive search for life just has to heavily prioritize them.
But applying the exo-IPM scattering framework to a red dwarf environment paints a chaotic picture of space weather. They aren't just smaller, dimmer versions of our sun.
Their internal physics are fundamentally different.
M-dwarfs are fully convective stars.
Fully convective. Explain how that differs from our sun.
In our sun, energy is generated in the core, it travels through a radiative zone, and only the outer envelope is convective.
Right.
But in an M-dwarf, the convection zone extends all the way down to the core. Superheated, boiling plasma circulates directly from the nuclear furnace at the core all the way to the surface in massive chaotic loops.
That sounds intense. That fully convective structure must generate incredibly powerful, wildly chaotic magnetic dynamos.
It does. And correlating the EXO-IPM framework to this environment indicates extreme plasma turbulence. Their stellar winds are far denser than our sun's, and their eruptive events are catastrophic by our standards.
So the coronal mass ejections and stellar flares from an active M-dwarf are exponentially more violent and frequent than anything our sun produces.
Yes, which highlights this massive paradox, the habitability versus detectability paradox.
Because astronomers get incredibly excited finding rocky, Earth-sized planets in the habitable zones of red dwarfs.
Naturally. Because the stars are dim, the zone where liquid water can exist is tucked very close to the star.
They might have oceans, a perfect climate for biology, the whole 9 yards.
But because that habitable planet is tucked in so close to a highly active red dwarf, it is constantly blasted by that exponentially violent space weather.
The EXO-IPM scattering model proves that while the planet might be perfectly habitable, the star's extreme plasma environment guarantees the complete spectrographic destruction of any radio signal that an alien civilization tries to send us.
They have water, but they're stuck in a permanent radio blackout of their own star's making.
A permanent radio blackout.
A civilization could be highly technologically advanced and transmitting continuously, but the inescapable disruptive medium of their own star's plasma permanently broadens their signal into invisibility.
It forces a complete recalculation of target selection in radio astronomy.
It has to. Prioritizing stars based solely on traditional habitability metrics, like rocky composition or liquid water, is no longer mathematically sound if our goal is to detect narrowband radio signals.
The habitability metrics must be cross-referenced with the star's localized plasma emission profile.
Exactly.
Okay, practically speaking, though, if an Earth-like planet orbiting an M-dwarf represents a significantly lower probability target for traditional narrowband searches, and we basically abandon the narrowband filters, aren't we just opening the floodgates to every random piece of cosmic noise?
That is the big question.
How do we actually filter for a smeared signal without drowning in false positives?
The 2026 study details the necessary implementation of dynamic time warping algorithms.
Dynamic time warping.
Yes. Instead of deploying single-channel match filters looking for an isolated spike, dynamic time warping algorithms are explicitly trained to recognize the spectrographic profiles of degraded, plasma-scattered signals.
Okay, so how do they do that?
They are programmed to search for a Gaussian-like spread of energy.
So instead of asking, is there a massive spike in channel A, the algorithm asks, is there an unnatural synchronized elevation of energy across channels A through Z that matches the mathematical profile of a signal smeared by a coronal mass ejection?
Exactly. The algorithm dynamically integrates power over a determined range of adjacent frequency channels. It hunts for the dispersed footprint, the widened shadow of a technosignature, rather than a singular spike.
It is designed to detect that thin, broad layer of energy the old algorithms just totally ignored.
Right. It represents a massive philosophical shift for the scientific community. We are moving from the concept of optimal transmission to the harsh reality of actual reception.
Because historically, we built detection machines based on theoretical perfection. We looked at what an extraterrestrial intelligence might optimally transmit to be energy efficient.
We assumed perfect logic.
But perfect logic doesn't account for boiling plasma.
No, it doesn't. The physical parameters of the intervening astrosphere absolutely must dictate the parameters of our reception.
It's a wild journey to think about. We started with the dream of the pristine alien beacon piercing the quiet dark, and we journeyed right into the turbulent reality of stellar astrospheres.
We've seen how EXO-IPM scattering physically shatters and smears photons, spreading their energy and dropping their peak amplitude,
causing traditional matched filter algorithms to fail entirely.
And the empirical calibration using the Voyager probes proved this smearing is a measurable, scalable fact. Our blind reliance on idealized models made our computational pipelines inherently blind to the realities of a very messy universe.
Which leaves us with a final chilling realization about the vast archives of astronomical data we've already collected.
Think about the decades of raw data sitting on hard drives in server farms right now.
Petabytes of radio observations. And for all those years, the historical algorithms were ruthlessly, systematically filtering out and discarding anything that wasn't a perfect narrow spike.
If the rigorous application of this ExoIPM broadening framework holds true, actual extraterrestrial technosignatures may have already been collected by Earth's observatories.
The signals might already be here,
Yes.
because their spectrographic profiles were physically smeared by the turbulent plasma of their home stars. The automated pipelines classified them as natural background noise.
The raw, uncompressed data of alien contact might literally be sitting in a digital archive right now.
Just waiting for the correctly calibrated ExoIPM scattering detection methodologies to be applied.
The whisper was there all along.
We just didn't know how to listen to the noise.